Alright folks, let's do number 24, and I hope you guys are finding this easier if you're in the class and you're watching these videos. At t equals 0, one toy car is set rolling on ow, on a straight track with an initial position at 15 centimeters, and its initial velocity is negative 3.5 centimeters per second. Alright, so let's draw this. So in fact, I'm going to draw this right here. Actually, so this is going to be the x-axis, and this is going to be maybe not necessarily to scale, but you know, just to get an idea. This is going to be 15 centimeters, and here's going to be some object, and some object is going to travel. Has an initial velocity at. Oh, it's rolling. I will actually pretend this is sideways, but whatever. Even though it's going downhill, rolling in some direction, we're just gonna tilt the horizontal axis. All right, let's draw this. All right. Notice that I did change this a bit. All right, so here an object is going to have some initial acceleration at 2.40 meters per centimeters per second square, and the initial velocity is going to be, and I'm not going to write the negative though, I'm just going to write the amplitude 3.5, even though I always write down the signs, but just as a tradition, I'm going to just do this for chapter 1 or 2, and then once we go to the later chapters, then we can change that. So this is going to be some initial velocity at 15 centimeters. So at t equals 0, this object is going to travel some initial velocity, and it's going to go in this direction, and then it's going to come back down to roll again. At the same time, another object is at 10 centimeters, and it has an initial velocity at 5.50 centimeters per second. Let's write that down. Centimeters per second. And it has a constant acceleration at 0, so it means that it's just going to travel at a constant velocity. At what time, if any, do the cars have equal speeds? Well, I encourage you guys to pause this video and to give this problem a shot, but we can already set up the equation for the object of 1. I'm going to use my traditional symbols now. So this is going to be my own notation that I'm going to be using. So the initial position is going to be so the final position is going to be some initial position, which I'm going to put 15 centimeters, plus the initial velocity, 3.50 centimeters per second, times time, plus 2.40 centimeters per second squared divided by 2 t squared. And let me change. So already this is going to be some object. The other object is going to be simply having the initial position at 10 centimeters added to 5.50 centimeters per second. Notice that I messed up. I put a plus, but here I'm going to compensate for the sign to put a negative, meaning the initial velocity being in the opposite left and the acceleration being towards the right side. And the question is asking, at the same moment, okay, at what time do the cars have equal speed? Well, this is just the position graph. I just wanted to set that up for you guys. The velocity, the final velocity of the object, it's for this vehicle, or for this object, is really just going to be some initial velocity, 3.50 centimeters per second, added to 2.4 centimeters per second square times the time. And this other velocity, it's always going to be at 5.50 centimeters per second. So for part A, in fact, let me move this out of the way here too. So these are your equations. So let's set the final velocity be equal to the object being 5.50 centimeters per second. Let's set since the part is asking for at what time does the object have equal speed, let's use this equation and say that this is going to be some initial velocity, 3.50 centimeters per second, plus 2.40 centimeters per second squared times the time. And here you solve for time. So this would be 9, I think, 9.00 centimeters per second divided by 2.4, is it? Yeah, it's 9.0 centimeters per second square. And let's get that TI-84 calculator. 9 divided by that would be 3 I think, is that the time I got? I don't remember anymore. T equals 3.75 seconds. That's the time when the slopes are parallel to each other on the graphs. So let's do part B now. What are their speeds? Oh my god, that's a retarded ass question. Okay. Well, since the one is a constant velocity, then we solve for the time where the velocity is the same, the speed is just going to be that. And since this starts at negative 3.50 centimeters and it's slowing down, I highly doubt it's going to reach farther than 5.50. So, all right. So, at what time, if any, do the cars pass each other? All right, let's answer that. I'm really trying so hard to like put the room here, but all right. So that's another way of saying when these two equations are equal to each other, and I forgot to put the t there, equal to each other. So I'm going to set it up as 10 centimeters plus 5.50 centimeters per second times the time equals 15 centimeters minus 3.50 centimeters per second times the time added to 1.20 centimeters per second square times the t square. So this is your equation. The only unknown is t. So all you have to do is solve for t. And there should be two answers because the graph is going to look like this. This is going to be the t-axis, and this is going to be the x-axis. One is going to start at 15 centimeters and 10. This 10 centimeters is going to have the velocity here at 5.50 centimeters. This other velocity is going to travel towards the left side in the opposite direction, and then it's going to catch up. And then this object is going to pick up acceleration, and it's going to eventually catch back up. So they're going to intercept at 2 points here. And I'm just going to give you the answer because this video is not going that great. So I don't know if it was recording, but the time that for the intersection is going to be 0.6 seconds, and it's going to intersect that's 13 centimeters, and the other one is 6.89, and that one's going to intersect at 48 centimeters per second. So these are the times that they intersect. At what are the locations at that time? Well, all you have to do is plug those two values in there. And here you're going to have x being 13.23 centimeters. And then this one is going to be 47. And keep in mind, folks, when I put these in the calculator, I always like to put the exact values. So that's just the way I roll. All right, so party, explain what the difference between the question A. Okay, that's such a retarded thing. Go F yourself. I don't care. How do I? Okay, the difference is that one is asking for the time when the velocity is the same, and then the other is asking for the time where they intersect. They're two different problems. I don't even know why it's asking. This is so retarded, to be honest. For a target audience of students who do not immediately understand the conditions are different, I'm just gonna say you're a retard. Forgive the language, folks, but if you really are just plugging and chugging, memorizing, and don't know what the heck you're doing, and you're just like randomly doing the problem because the teacher tells you to do this step and that step and this step, and you do that step and you do this step and you do that step, and you don't understand what the problem is saying or even interpret it, or you haven't have a little bit of common sense, presuming you're not a math literate. If you are, then that might be a little different story. then I can understand that. But if you're at this level of physics and you're giving two problems that I just solved for you guys, and you have to ask they're not that's not the you have to ask what's the difference between these two problems. Then I literally think you're retarded, folks. Like, you have to be retarded to not know the difference. So I don't get it. I don't know. I don't even know how to answer this, to be honest. I'm not a traditional YouTuber, so I'm just gonna say I don't know. Yeah. Yeah. Get points off for that. Don't really care. All right.